Hey everyone, we've talked about sums of finite series, but not every series is going to be finite because not every sequence is finite. Sequences can go on for forever and ever and ever, so we could keep adding the terms to them. So we can have infinite series. Oops. The most common way to express this is with sigma notation and putting an infinity on top because that tells us where we're ending. So if it's ending here, that means it's not ending. It's going forever and ever. Now, let's say we had a sub k was an arithmetic series. So let's say it was just like a 2k plus 1. What this is saying is we're doing 3 plus 5 plus 7 plus 9, and it just keeps going and going and going forever. So if we have an arithmetic sequence and we're trying to find the series for that arithmetic sequence, and it's an infinite series, it doesn't look like this is going to work. We're constantly adding something bigger and bigger. We're constantly getting further away from 0. And if d was negative, you'd be getting further away from 0 in the opposite direction. So if it's an arithmetic sequence that you're trying to find the series of, there is no sum. We do not say that it adds to infinity or adds to negative infinity. We say that there is no sum. Because nothing adds to infinity. Nothing adds to negative infinity. It's just not adding to anything. It just keeps going and going and going, but infinity is not a solution. All right. We can say things approach infinity. We can say things go towards infinity, but you're never reaching infinity. If we're doing a sum, that means it equals something. All right. I don't know why I erased that and didn't just change slides. Whatever. Now let's talk about a geometric series. So let's say we have the sum from k equals 1 to infinity of 2 times 2 to the k minus 1. Well, this is telling us 2 is our first term. We're multiplying by 2 every time. Uh-oh. We're running into the same problem as we did with the arithmetic. 2 plus 4 plus 8 plus 16. We just keep adding bigger and bigger numbers on. So it would be going towards infinity but not reaching infinity. So again, this one's no sum. But this isn't always going to be the case for a geometric sequence. If we're doing the series of a geometric sequence, like this one, this time, our first term is 2, then times 1/2 plus 1, times 1/2 plus half plus 1/4 plus 1/8, so on and so forth. This one is going to equal something. And I'm going to show on a number line how that works. So before we start the sum, we're at 0. And then our first jump, we go to 2. Our second jump, oops, that'll be 3 on the number line. It's 1, brings us to 3. So just by scale, this would be 4, that's 1. So after 3, it's 1/2, so it's 3.5. Then after 1/2, it's 1/4, Ah. Then after 1/4, it's 1/8. Then after 1/8, it's 1/16, then 1/32. So every single time, we're covering half the distance from 0 to 4. So half the distance from 0 to 4 the first time is 2. Then half the distance from 2 to 4 is 1. Then half the distance from 3 to 4 is 1/2. Half the distance from 3.5 to 4 is 1/4. Then half the distance from 3 3/4 to 4 is 1/8. Half the distance from 3 7/8 to 4 is 1/16, so on and so forth. So we're cutting the distance in half. We're getting closer and closer to 4. And it gets so infinitely close that we just say that the sum is 4. It doesn't actually reach it, but it is so close that we just say it's 4. So that's how we can find the sum of an infinite sequence. Now, if we look at this, if we look at these two sequences, try and grab my marker, there we go. It's all about what R is. In this case, R, I'm going to say the absolute value of R is greater than 1. In this case, the absolute value of R is less than 1. When your absolute value of R is less than 1, you can find the sum. This type of sequence is called, this type of series is called a converging series. A converging series has a sum. It's approaching a value. If it doesn't have a sum, this is called a diverging series. So a converging series approaches a value. A diverging series does not approach a value. Another way to tell if a series is converging or diverging is by observing the limit, the end behavior rather, of the explicit definition. So the limit as k goes to infinity of 2 times to the k minus 1, that's an exponential, and it's going up. It behaves like this. That's how it looks. So that's infinite. If your limit of your explicit definition is infinity or negative infinity, it's diverging. If your limit is a finite value, in this case, it's 0, it's converging, because the graph would look like that. So if the end behavior is infinity or negative infinity, it's a diverging series. If it approaches a finite value, it's a converging series. Now, it'd be nice if we had a formula for this. Well, we have a formula for a finite. So if it's just from 1 to n of a sub k, it's a sub 1 times 1 minus r to the n all over 1 minus r. But if we change that to infinity up top, a sub 1 doesn't change, r doesn't change, but this n does. This n is infinity. Now I know we can't really plug in infinity, but I'm just putting it there to think about it conceptually. Now, if we are finding the sum, the infinite sum, the only way that can happen is if r, the absolute value of r, is less than 1. So if the absolute value of r is less than 1, if you're raising r to a power, you're multiplying something less than 1 by itself. So it's getting smaller and smaller and smaller. So if you keep multiplying it by itself and making it smaller and smaller, it's going towards 0. So essentially, this term is 0. So it's a sub 1 times 1 minus 0. That's just a sub 1. And then over 1 minus r. So this is our formula for an infinite geometric series. Oops. All right. So that's it for arithmetic and geometric series. Stay tuned. We'll have some more information for you guys in the not too distant future. Bye.